Germany offers a broad spectrum and a richness in business opportunities for foreign companies to tap the growing market of hydrogen in Germany.
As the world races toward a post-fossil fuel future, electric vehicles have become the poster child of clean mobility, but they may not be the final answer for every road, load, or climate. While battery-powered EVs dominate headlines and investments, Germany is quietly hedging its bets with a parallel track: hydrogen-powered engines. Through aggressive funding, pioneering prototypes, and strategic industry collaboration, the country is reimagining transportation with a focus on hydrogen technology. This is no hyperbole. Germany's new hydrogen engine technology will destroy the entire EV industry forever. Well, at least that's the plan. Let's see how it will work out. Germany's hydrogen engine developments. Back in June 2020, the federal government of Germany unveiled its national hydrogen strategy, allocating €9 billion to accelerate hydrogen production, distribution, and application across key sectors. Of this, €7 billion was earmarked to stimulate the domestic market and industrialize green hydrogen technologies, while €2 billion was designated for fostering international partnerships. The strategy marks a significant pivot in Germany's long-term climate goals and is directly aligned with broader EU objectives, including the European Green Deal and the Fit for 55 legislative package, which targets a 55% reduction in greenhouse gas emissions by 2030 compared to 1990 levels. Green hydrogen, produced via electrolysis powered by renewable energy sources like wind and solar, is central to this initiative. Unlike grey or blue hydrogen, which involve fossil fuels and carbon capture, green hydrogen offers a carbon-neutral path for decarbonizing hard-to-electrify sectors such as heavy industry, logistics, and long-haul transport. A key target of Germany's hydrogen roadmap is the mobility sector, where the limitations of battery electric vehicles, particularly in range, charging times, and suitability for heavy-duty use, create space for hydrogen technologies to thrive. German automakers are leveraging hydrogen to future-proof their relevance in a rapidly evolving market. BMW, for instance, has emerged as a leader in the hydrogen mobility space through its development of the iX5 Hydrogen, a fuel cell electric vehicle or FCEV based on the existing X5 SUV platform. The vehicle, first revealed at the IAA Mobility Show in Munich in 2021, is the result of a long-standing partnership with Toyota, which supplies the core fuel cell stack used in the prototype. The iX5 Hydrogen has a range of around 500 km, refuels in under 5 minutes, and emits only water vapor. BMW began producing a small series of these vehicles in December 2022 at its pilot plant in Munich for global demonstration. Beyond fuel cells, BMW is also investing in hydrogen combustion technology, known as H2 ICE. Unlike fuel cells, which convert hydrogen into electricity via electrochemical reactions, H2 ICE systems use modified internal combustion engines to burn hydrogen directly. This approach leverages existing manufacturing capabilities and could offer a more seamless transition for certain vehicle categories. In the commercial transport sector, MAN Truck & Bus, a subsidiary of the Volkswagen Group, is spearheading hydrogen combustion engine development for heavy-duty logistics. MAN's upcoming hydrogen trucks are designed to address the energy demands and operational patterns of long-haul freight, where battery weight and recharging times pose significant barriers. In March 2023, MAN announced it would begin real-world testing of its H45 hydrogen combustion engine in partnership with key logistics providers by 2025. The engine uses port fuel injection with spark ignition and operates with zero carbon dioxide emissions when powered by green hydrogen, though some nitrogen oxide emissions still occur. These can be mitigated using standard exhaust after-treatment technologies. Simultaneously, Daimler Truck, the commercial vehicle division of Mercedes-Benz Group AG, is focused on fuel cell technology. Its flagship project, the Gen H2 truck, uses liquid hydrogen for improved energy density and greater range, over 1,000 kilometers per fill. Designed specifically for long-haul operations, the GN H2 truck is being developed in partnership with Volvo Group under a joint venture called Cellcentric, founded in 2021 to build large-scale fuel cell systems for trucks. Daimler conducted initial prototype testing in 2021, and full customer trials will follow, with series production planned for 2027. The use of liquid hydrogen, stored at -253 degrees Celsius, offers logistical advantages over compressed hydrogen gas, particularly for cross-border freight routes requiring extended range. In the background of all this innovation, Bosch, one of the world's largest automotive suppliers, plays a pivotal enabling role. The company is heavily investing in both fuel cell systems and hydrogen production technologies. In May 2022, Bosch announced a €500 million investment in solid oxide fuel cells for stationary applications, and another €1 billion through 2024 to develop and manufacture mobile fuel cell systems for vehicles. Bosch has also partnered with PowerCell, Sweden AB, and Ceres Power to advance its technological capabilities. Additionally, Bosch is developing hydrogen electrolysis systems to support green hydrogen production, with pilot projects underway across Germany and other EU countries. The company's involvement across the value chain, from production and compression to fuel cells and storage, positions it as a key player in scaling hydrogen adoption throughout Europe. If infrastructure and production costs can be brought in line with economic realities, Germany could lead in the global hydrogen economy. So, what is it that we're actually talking about? Let's dive deeper. Types of hydrogen engines. Hydrogen-powered vehicles fall into two primary categories: hydrogen fuel cell electric vehicles, or FCEVs, and hydrogen internal combustion engine vehicles, or H2ICEs. While both rely on hydrogen as a fuel, they diverge in how it is converted into usable energy. FCEVs convert hydrogen gas into electricity through a chemical reaction with oxygen inside a fuel cell stack. This electrochemical process, known as reverse electrolysis, produces electricity, water vapor, and heat as byproducts. The electricity powers an electric motor which drives the vehicle, just like in traditional battery EVs. However, unlike EVs that draw power from large lithium-ion batteries, FCEVs generate electricity on demand from hydrogen stored in high-pressure tanks. The architecture typically includes a smaller lithium-ion battery, or supercapacitor, to handle peak power demands and regenerative braking. But the primary energy source is the hydrogen fuel cell. A leading example of FCEV technology is the BMW iX5 Hydrogen, a hydrogen-powered variant of the X5 SUV. It features fuel cell stacks supplied by Toyota, which has over a decade of experience in hydrogen mobility through its Mirai model. The iX5 Hydrogen achieves a range of around 504 kilometers or 313 miles under WLTP standards, with hydrogen tanks capable of refueling in under 5 minutes, providing an edge over battery EVs in terms of turnaround time. Another global benchmark is the Hyundai Nexo, which offers a similar range and has been available commercially since 2018. In Germany, these vehicles benefit from growing but still limited refueling infrastructure, with about 100 hydrogen stations operational presently, the largest network in Europe. FCEVs are particularly suited to use cases where range, weight, and quick refueling are critical. For example, commercial trucks, buses, and intercity coaches benefit significantly from the high energy density of hydrogen. Daimler Truck's Gen H2, a fuel cell truck designed for long-haul freight, runs on liquid hydrogen stored at cryogenic temperatures and targets a driving range exceeding 1,000 kilometers. Similarly, the Toyota Hino and Hyundai Xcient fuel cell trucks are examples of growing global momentum in FCEV logistics. In contrast, hydrogen internal combustion engines, or H2ICs, burn hydrogen directly in modified versions of traditional combustion engines. They rely on spark ignition, similar to petrol engines, and can operate with relatively minor modifications to existing engine platforms. H2ICs emit no carbon dioxide because hydrogen contains no carbon atoms. However, due to the high-temperature combustion process, small amounts of nitrogen oxides may be produced. These emissions can be mitigated using standard after-treatment systems like selective catalytic reduction and exhaust gas recirculation. MAN Truck and Bus, based in Munich, Germany, is at the forefront of developing H2ICE for commercial applications. In March 2023, the company revealed its H45 hydrogen engine, built on a 13-litre diesel platform and adapted for hydrogen combustion. The engine is being developed specifically for long-haul logistics, where battery electric solutions are less feasible due to payload penalties and charging time constraints. MAN plans to deploy the first test fleet soon, targeting logistics firms that can refuel centrally, thereby overcoming the sparse hydrogen infrastructure issue. The company is focusing on gaseous hydrogen at 350 bar, which is easier to handle than liquid hydrogen, but offers slightly lower energy density. Another major proponent of H2ICE is Toyota, which began public road testing of hydrogen combustion vehicles in 2021, using a modified Corolla Sport hatchback in Japan. In Europe, Toyota and Yamaha are collaborating to develop a 5-litre V8 hydrogen engine, aiming to maintain the performance and acoustic appeal of combustion powertrains while eliminating carbon dioxide emissions. Meanwhile, BMW is reportedly conducting internal R&D on hydrogen combustion options, particularly for performance or motorsport applications. The appeal of H2ICE lies largely in its compatibility with existing engine manufacturing infrastructure, which makes it a more cost-effective, short-term solution than fuel cells, especially in markets where engine production capacity is already established. Moreover, H2ICE engines can be serviced using familiar tools and techniques, lowering the barrier to entry for fleet operators and mechanics. However, the overall efficiency of hydrogen combustion, which is around 25 to 30%, is significantly lower than that of FCEVs, which offer an efficiency of up to 60%, or battery EVs, which boast numbers about 85 to 90%, making it less attractive for energy utilization unless hydrogen is abundant and cheap. So, can these hydrogen vehicles beat EVs? Well, let's dissect the facts, shall we? Advantages of hydrogen engines over EVs. Hydrogen engines offer several key advantages over battery electric vehicles, especially in use cases where speed, endurance, and load capacity are critical. As countries like Germany push towards zero-emission transportation, these strengths make hydrogen-powered systems an increasingly attractive complement, and in some cases, an alternative to conventional battery-driven mobility. One of the most significant advantages of hydrogen vehicles is their rapid refueling time. Where battery electric vehicles typically require between 30 minutes and several hours to charge, depending on the capacity of the battery and the charger used, hydrogen fuel cell vehicles, or FCEVs, can refuel in approximately 3 to 5 minutes. This parity with traditional gasoline or diesel refueling times makes hydrogen particularly suited for applications that rely on high uptime and fast turnaround, most notably commercial fleets, buses, taxis, and long-distance trucks. For instance, BMW's iX5 hydrogen prototype, developed with Toyota, uses high-pressure 700-bar hydrogen tanks that can be refilled in under 5 minutes and deliver up to 504 kilometers of range. Similarly, Hyundai's Nexo and Toyota's Mirai FCEVs both boast refueling times below 5 minutes. This rapid refueling capability is invaluable for operations like long-haul logistics and public transit, where time is literally money. Hydrogen vehicles also generally offer greater and more stable driving range than many battery EVs, particularly under real-world conditions. FCEVs routinely achieve ranges between 500 and 700 kilometers, depending on the size of the hydrogen tank and the efficiency of the fuel cell system. For example, the second-generation Toyota Mirai, launched in December 2020, offers up to 650 kilometers on a full tank. Moreover, hydrogen's energy density does not degrade as sharply under extreme temperatures. Battery EVs often lose 10 to 30% of their range in cold weather due to lithium-ion chemistry performance drops and increased cabin heating demands. In contrast, FCEVs perform more consistently in cold climates because the chemical reaction in fuel cells generates heat, which can be used to warm the cabin without drawing significant energy from the propulsion system. This consistency makes hydrogen propulsion more reliable in places with harsh winters. Another major benefit lies in the weight advantage of hydrogen systems over batteries, especially in heavy-duty vehicles. Batteries become disproportionately large and heavy when scaled to meet the energy demands of commercial trucks, buses, or trains. For example, an electric truck capable of 800 kilometers of range may need a battery pack exceeding 1,500 kilograms, significantly reducing payload capacity and impacting vehicle efficiency. By contrast, hydrogen tanks and fuel cell systems provide high energy density with far less mass. Daimler Truck's Gen H2, using liquid hydrogen, targets a range of over 1,000 kilometers while maintaining a vehicle weight close to that of diesel trucks. This weight efficiency makes hydrogen better suited to industrial machinery, rail freight, and construction equipment, where hauling heavy battery packs is neither practical nor economical. In addition to logistical advantages, hydrogen engines reduce geopolitical and environmental dependency on critical raw materials, particularly those used in lithium-ion batteries. EV batteries rely heavily on lithium, cobalt, nickel, and rare earth elements, materials that are not only finite and expensive to extract, but also concentrated in politically sensitive regions. For example, more than 60% of the world's cobalt comes from the Democratic Republic of Congo, while China dominates the global supply chain for rare earth processing, controlling around 80 to 90% of refining capacity. These dependencies create both strategic vulnerabilities and ethical concerns, especially regarding labor practices and environmental degradation linked to mining. In contrast, hydrogen fuel cells use platinum as a catalyst, still a rare material, but used in much smaller quantities, and with ongoing efforts to reduce or replace it entirely through next-generation cell designs. Hydrogen combustion engines, or H2ICs, on the other hand, use mostly conventional components already found in internal combustion engines, requiring no lithium or cobalt at all. Moreover, hydrogen can be produced domestically and renewably, reducing dependence on imported fuels and contributing to national energy sovereignty. Germany's National Hydrogen Strategy, launched in 2020 with a €9 billion budget, aims to establish green hydrogen production using wind and solar power, further reinforcing the country's climate and security objectives. This is aligned with the European Union's RE-Power EU plan, which targets the production of 10 million tons of renewable hydrogen by 2030, alongside the import of another 10 million tons. With electrolysis technology improving and electrolyzer costs expected to fall by up to 70% by 2030, hydrogen's role in decarbonizing transport, industry, and energy storage is becoming increasingly viable. As infrastructure expands and green hydrogen production scales up, hydrogen engines are positioned not just as niche alternatives, but as foundational technologies for the next phase of decarbonized transport. But this is still a work in progress, infrastructure and production hurdles. Despite their growing potential and numerous advantages, hydrogen vehicles face a series of infrastructure and production hurdles that currently limit their widespread adoption. Green hydrogen, which is derived from water electrolysis powered by renewable energy sources like wind and solar, costs between 4 and 7 euros per kilogram, compared to 1.50 to 2.50 euros per kilogram for grey hydrogen, which is produced using fossil fuels such as natural gas through steam methane reforming. This cost disparity not only hinders the competitiveness of green hydrogen, but also undermines its environmental benefits when cheaper grey hydrogen is used instead. According to the International Energy Agency, more than 95% of global hydrogen production still comes from fossil fuels, contributing approximately 830 million tons of carbon dioxide emissions annually, roughly equal to the emissions of the entire aviation industry. Germany, under its 2020 National Hydrogen Strategy, aims to shift this paradigm by producing up to 5 gigawatts of green hydrogen capacity by 2030. Distribution and storage of hydrogen present additional obstacles. Hydrogen is the lightest and smallest molecule, which makes it difficult to contain and transport efficiently. It must be either compressed to 350 or 700 bar for gaseous storage or liquefied at minus 253 degrees Celsius for cryogenic transport, both of which require significant energy input and specialized infrastructure. These conditions complicate the logistics of delivering hydrogen from production sites, often located far from urban centers or industrial hubs with ample renewable energy, to refueling stations. In Germany, there are just over 100 public hydrogen refueling stations. These stations are largely concentrated along major transport corridors and in cities like Berlin, Hamburg, Munich, and Frankfurt, leaving vast areas, especially in eastern and rural Germany, without access. By contrast, there are more than 90,000 electric vehicle charging points across the country. Another issue stems from the cost and market availability of hydrogen-powered vehicles. Currently, the production of fuel cell electric vehicles and hydrogen internal combustion engines remains expensive due to low volumes and specialized components. For example, the Toyota Mirai, one of the most widely available FCEVs, is priced at around 63,900 euros in Germany, significantly higher than many comparable battery EVs. Part of the cost premium arises from the use of platinum in fuel cells, high-pressure carbon fiber tanks, and the need for precision engineering in the fuel cell stacks. Even as companies like BMW, Hyundai, and Honda explore next-generation fuel cell designs to reduce platinum dependency, economies of scale have not yet materialized to drive prices down meaningfully. Market availability remains constrained as well. Presently, only a handful of hydrogen vehicles are available for consumers in Europe, including the Toyota Mirai, Hyundai Nexo, and limited test fleets like BMW's iX5 Hydrogen, which is not yet available for public purchase. In addition, the financial and regulatory incentives currently favor battery EVs, creating an uneven playing field. Germany's broader ambitions for hydrogen mobility hinge on resolving these interconnected challenges. The Highland Programme, initiated by Germany's Federal Ministry of Transport and Digital Infrastructure, aims to fund hydrogen model regions with pilot projects that integrate production, infrastructure, and vehicle deployment. Similarly, the EU-backed IPCEI Hydrogen Project, which is short for Important Project of Common European Interest, allocates funding for infrastructure expansion across borders, including hydrogen corridors for trucking between Germany, the Netherlands, Austria, and France. As the EU moves to ban new petrol and diesel cars by 2035, hydrogen-powered vehicles present a strategic opportunity to fill critical gaps left by battery EVs. While BEVs are expected to lead in private transport, they face challenges in sectors needing fast refueling, longer ranges, or reliable performance in extreme conditions. Hydrogen fuel cell electric vehicles offer fast refueling, better ranges, and stable output in cold weather. Major companies like Daimler Truck, MAN, and Volvo are trialing hydrogen trucks, while Toyota and BMW are developing H2ICs for enthusiasts. Germany is investing €9 billion through its national hydrogen strategy, aiming for 10 gigawatts of green hydrogen capacity by 2035. Programs like Highland and partnerships with Bosch and Linde are building regional hydrogen hubs and refueling networks. Hydrogen also supports grid stability by storing surplus renewable energy, easing strain from rapid EV adoption. Naturally, it is poised to serve niche markets like long-haul freight, remote communities, and industrial mobility. And it will also take a bite out of the EV consumer pie. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.